Now that we've discussed how to graph polar functions, we're going to talk about how to use calculus to calculate the area inside or bounded by a polar curve. So we're going to use this basic formula. We have the area equals 1/2 times, we're going to integrate from alpha to beta of r squared d theta. So in order to obviously to do these areas, we need to be able to graph these things. And we look at this, r equals 2 plus 2 sine theta. When we graph this, we know it's going to have y-axis symmetry. We got a cardioid that looks something like that. All right, so we need to be able to think about where these locations on the graph occur. Okay, we're here when theta equals 0. We're here when theta equals negative pi over 2. And we're up here when theta equals pi over 2. So one of the overriding concepts here is that we want to utilize symmetry of these shapes as much as possible. All right. So when I look at this shape, if I can calculate just the area here, then I can find the entire area just by doubling that. Right. So the area is equal to, the shaded area here is equal to 1/2. We're going to integrate from negative pi over 2 to pi over 2 r squared d theta. So that is 2 plus 2 sine theta squared d theta. Alright, that's going to give us this shaded region. So for the entire area bounded by this graph, I need to double that. Alright, so for these examples in these notes, I'm just going to do the setups. I'm going to leave this for you to do as an exercise, so work this out. We can certainly talk about it in class. When you work that out, substitute your upper and lower limits in there and double it, you'll end up with this area of 6 pi. Alright, so let's take a look at the next example. We want to find the area of one petal of r equals 2 sine 3 theta. So we need to be able to graph this first. Alright, it's going to have 3 petals. If I think about how these petals are going to be oriented, I need to know when sine of 3 theta is going to equal 1. Alright, that's going to happen when 3 theta equals pi over 2, so that's going to happen when when theta equals pi over 6. So we're going to get our maximum petal length at pi over 6, and then they're going to be evenly distributed around that 360 degrees, or 2 pi radians. So we're going to have a petal length of 2, so that's going to look about like this. Alright, so my radius is 0 when theta equals 0, and it reaches its longest length while theta becomes when theta is pi over 6, I get my r equals 2, so I get out to the maximum there. Right? I've been asked to find the area of one petal, so I'm going to calculate the area of half a petal and then double it. So I'm just going to integrate from 0 to pi over 6 of r squared. That's 2 sine 3 theta squared d theta. and then to find the area of an entire petal, I'm going to double that. So really the 2 and the 1/2 just cancel out here. All right. If you work through that, square this up, work the integration. If you do this one by hand, a double angle formula will come in handy. You're going to get a sine squared of 3 theta, and the easiest way to integrate that is to rewrite it as 1 minus cosine of 6 theta over 2. So the double angle formula will come in there, and the total area ends up being pi over 3. All right, in the next example, we want to find the area of one petal of r equals 4 cosine 2 theta. So we have to think about what this graph is going to look like. We have 2 theta, so we're going to have 4 petals. So we want to find the area of one petal. In this case, I am going to start not pi, sorry. That is theta equals 0 at r equals 4 the first time. And then as we progress up here, I'm going to get theta equals pi over 4 when r's, that's going to create an r equal to 0. Because we have cosine of pi over 2 will give us a 0, and then we'll have a radius of 0. So I'm going to integrate here. I'm going to find half of one of the petals. So 1/2 times, I'm going to integrate from 0 to pi over 4 r squared. So 4 cosine 2 theta squared. That gives me the area of half a petal, so I'm going to double that. That'll give me the area of one full petal of that graph. And if we work through that integration again here, a double angle formula comes in handy, and your total area is going to end up being 2 pi for that problem.